Before we start doing calculations with real numbers, going through examples, I wanted to give you an overall conceptual framework for how ANOVA works. Let's start by comparing and contrasting the analysis of variance with t-tests, which is what we saw in an earlier lecture. Now, t-tests can be used to compare two means and determine if they're statistically significantly different from each other. And we do that by computing the t-test statistic, which is based on the size of the difference between the means of those two groups and the size of the standard error associated with that difference. Now, the t-test statistic, the exact formula really depends on if this is a one sample or two sample t-test, if it's a paired sample, whatever, but this is the essence of the t-test. Now, ANOVA, which is for comparing three or more group means to see if they're statistically significantly different, uses the F-test statistic. And the F-test statistic uses essentially, you need to calculate variances. You calculate variances from two sources of data. You calculate between group variance, you calculate within group variance, and you compare the two. Okay, so now let's take the rest of the lecture to focus on what that is exactly. Let's remember the null hypothesis for essentially all of the statistical tests that we do in this course, which is that all the experimental data that we collected, regardless of the number of factors, the number of treatments, the number of factor levels, all of that experimental data can be described with one curve, with one distribution, not multiple curves or multiple distributions for different groups. Okay, just one curve. The averages of the groups, our group means, are not statistically significantly different from each other. And the reason why there might be slight differences from one group to another isn't because of any underlying true difference, but just random sampling error. So, for example, if you have three herbicides that you're testing, three groups essentially, and you're looking at the percentage of weed reduction, and if there's a significant difference between the three herbicides you're testing, well, the null is going to say there's no true difference, but your average, your sample mean of the three herbicides, they're not going to be exactly the same. They might be a little bit different. And that's, again, because of this random sampling error. The other thing that is going to necessarily be true, and you might have not thought of, is that the variance should also be the same. Remember, a distribution, for a normal distribution, to describe a normal distribution, we need a mean and we need a standard deviation. And that's a measure of variation. So the variation between, say, percent weed reduction should be the same in group A or herbicide A and herbicide B and herbicide C. The variation should be essentially the same. Now, they might be, again, a little bit different, herbicide A versus B, because of sampling error, but they're all fair estimates of the true underlying population variation that is common to all three groups of herbicides. So, just to reiterate, if our null hypothesis is true, then our groups share both the same average, the same mean, and the same variation. So this is why variance is important with F-tests and ANOVAs, because our variances of our groups should essentially all be the same. There might be some sampling error, right? They're not going to be exactly the same, but they're all fair estimates or predictions of the one true underlying variation or standard deviation that describes the whole population. So, before I explain in a little bit more detail how we go about doing that and testing that with the F-test, I want to remind you the difference between group and within group variation. So, within group variation has to do with variation in the variable of interest that we're measuring, be that grain yield or percent weed reduction or milk production per cow, within a given group. So within the unfertilized control or within herbicide A or within the Prolac supplementation group. What is the variation just within that group? That's within group variation. And we can calculate within group variation, obviously, for every single group in our experiment, every single treatment, every single factor level. Now, we also have between group variation, which has to do with variation across groups between group A and group B, or group A and group C, or however many groups we have. So we have between and within variation. And we can calculate between and within variation for almost all of the statistical tests that have three or more groups. Now I can describe conceptually what's going on when we do an ANOVA, when we perform an F-test. So here's an example of an ANOVA, or really a data set with four different groups, four treatments or four factor levels. And for each group, we can calculate the within group variation. Let me just pull that up here. We can calculate the within group variation, as you can see these yellow arrows. We can also calculate the between group variation. And in ANOVA, we do that in a specific way. We calculate first the grand mean, or the mean of the whole data set, the average value of all four groups combined. And we compare the mean of the whole data set to the average variation between groups. So between the mean of group 1, 2, 3, and 4 to the grand mean, the mean of the whole data set, as you see in the green arrows. So this is really what we're doing when we do an F-test. We calculate variation in these two different ways, between group and within group. And if our null hypothesis is true, these are two ways to estimate the same thing, the true underlying population variation. So if our null hypothesis is true, then our mean within group variation and our mean between group variation should be essentially the same. Now this is our F-test statistic when we're dividing the between group variation by over the within group variation. And if our F-test is equal to 1, then we would fail to reject our null hypothesis because the variations are exactly the same, which is what we would expect if our null hypothesis is true. So the larger our F-test value is, the more different it is from 0, the less likely our null hypothesis is true, and the more likely we will reject our null hypothesis. So again, the F-test is just a ratio. Sometimes you'll see this called a variance ratio because we're just comparing the variance of two different variances. And if our null hypothesis is true, these variances should be the same. So let's run through an F-test. And you can see here on the right the F distribution. It looks different than the T distribution. I'll talk a little bit about the shape of the F distribution, but let's first calculate our F-test statistic because that's the first step. So we calculate between group and within group variation. We divide one by the other, and our F-test statistic is equal to 5.65. Now we have to compare our F-test statistic to our critical F-test value, which is largely dependent on our significance level. So here our significance level is 1% or an alpha equal to 0.01. So we have our critical F-test value. We compare it to our F-test statistic, and our F-test statistic is greater than our critical F-test value, and so we reject the null hypothesis. We say that, the fact that our between group variation is 5.65 times larger than within group variation, because that's what that F-test statistic is saying, that is that would not happen by chance. And so we're going to reject our null hypothesis. So that is the essence of your F-tests, and F-tests underpin ANOVAs. So our null hypothesis, our overall null hypothesis, is that there is one distribution that can describe all the data in our experiment, and there's one mean. That distribution has one average or mean value, it has one variance. And if that is true, if the null is true, then your between group variation and your within group variation are going to be equal. And so that is what the F-test is looking at specifically, that your variances between group and within group are the same because they're both estimating the same population level variation. So you compare your F-test to your critical F statistic, and you either reject or fail to reject your null hypothesis. A bit about the shape of the F distribution. So it's hump-shaped and asymmetric. So the hump, the highest point of the F distribution, is where F is equal to 1, because that is the null hypothesis, that the variances are equal. And it's asymmetric because there's a long tail. Now, the exact shape of the F distribution will depend on the number of degrees of freedom of both the numerator and the denominator, similar to the t-test or the T distribution, although that really only had one dependent on one form of degrees of freedom, the sample size. And you can encounter the F-test outside of ANOVAs because it's used whenever you're comparing two variances, if you want to know if two different variances are statistically similar or not.